Hello and welcome everyone. This video is about inverse quadratic interpolation. The importance of this method is that it is used in another more efficient and reliable root finding method, which is known as Brent's method, and which will be the topic of the next video. Just to recap, if we have a function f of x, then all values of x for which f of x is equal to 0 are called the roots of this function. Now suppose that f is locally invertible around the root, then we can write f inverse of y is equal to x, which means that this inverse function, when evaluated at y is equal to 0, will give us the root of the function f of x. The method involves quadratic interpolation, so it requires the user to input 3 initial points. Then the root estimate for the next iteration is obtained using Lagrange's 3-point interpolant, in which the roles of x and f are interchanged and x is evaluated at f is equal to 0. We stop the iterations if a stopping criterion is met, otherwise we drop the oldest point, that is xk minus 2, shift the position of xk and xk minus 1 to xk minus 1 and xk minus 2 and add xk plus 1 as xk and repeat the process. This method, when used independently, can sometimes be unreliable. This is because if the 3 initial points are not well chosen, it can lead to divergence or poor convergence. There is no bracketing guarantee if initial guesses are too far from the root. And the quadratic polynomial poorly approximates the function when the function values at the points are too close, causing stability issues. Let's see how we implement this in Python. We can write a function whose inputs include the nonlinear function f and 2 points, that is interval start and end. You can provide 3 points instead. I am choosing the third point randomly between these two values, but as I said, you can use any other methodology. The key thing is that the method needs 3 starting points. I then check if any of the 2 points are equal. If they are, then we return none, as the points need to be distinct. And then on line 2 to 9, we check if any of the function values already satisfy the threshold criterion. If yes, these represent the root values. Then, in a while loop, we compute the next estimate using Lagrange's interpolation formula. Check for convergence. If we are to continue, then update current, old, and older values and continue until a stopping criterion is met. We use this method on a function x cubed minus 1 to find its roots, and we were able to find the real root, that is x is equal to 1, successfully in this case. This concludes the video. Thanks for watching. Don't forget to subscribe to my channel and see you in the next video.